Hi, I'm Tommaso, PhD student at Graz University of Technology.
And I'm Daniel, also a PhD student at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
Do you know what I think our friendship is like?
Oh no, this sounds like the opening for a quote-unquote funny pun.
Well, it's like iron, very stable, the most tightly bound of friendships.
Such a great joke, why don't you explain it?
Well, the fact is that iron is the one element in the periodic table with the highest binding energy, meaning that fusing two iron nuclei together to get something heavier is energetically unfavorable.
Apparently you took my obviously ironic suggestion serious. I mean, it's kinda interesting, but still not funny.
Oh god, ironic? That was a Tommaso joke.
Damn it, shame on me.
Ironclad explanation from my side, don't you think?
Yeah, kinda.
I mean, maybe you were expecting more jokes, right? Like a much heavier amount of them.
This is what I feared, yes.
Okay, but well, luckily for you, I decided to fuse them together, so it's more difficult to break them from your side.
I'm hardly lucky, and there's nothing to be broken here.
Come on, even if you look skeptical now, I think that one day my jokes will finally sink in and you'll start glowing like hot plasma with their understanding. Finally, they will spark something in you and you lose all your negative charges, vibes towards them.
I so wish that lack of understanding were the issue.
Oh, come on, one day you'll be positively charged by my jokes. Ionized, I dare say.
If that ever were to happen, you know that I lost my grip on reality.
Alright, so much drama. Well, as our listeners might have guessed now, today we'll be talking about plasma physics, and with us to discuss about it, Christopher Albert, professor at Graz University of Technology.
And as always, we asked our friends and students what they know about plasma physics, and that is what they had to say.
I know that plasmas are like a gas, but so hot that electrons and cores of the atoms have gotten separated. And so in addition to the usual description of gases, you need to take into account their charge through the Maxwell equations. And I also know that they are a very important component of nuclear fusion reactors, although I don't really know why that is.
So today on the podcast we have Christopher Albert. Christopher is a professor at Graz University of Technology. So Christopher, welcome. And can you introduce yourself, your background, studies, field of expertise? Stage is yours.
Yeah, so I studied physics at TU Graz also. I started in laser physics for my bachelor thesis, then I saw I should do theory, and then I entered acoustics at a more industrial application, and then I decided I want to do something for humanity, so I got a PhD in the field of nuclear fusion and theoretical plasma physics. Yeah, and since then I've spent some time in Germany at the Max Planck Institute for Plasma Physics as a postdoc, and then was lucky to come back as an assistant and now associate professor in Graz.
So you mentioned plasma physics, and I guess most people maybe at some point heard about plasma, but could you explain what this actually is?
Yeah, plasma is a state of matter where the electrons and the ions are separated in contrast to a usual gas, and this gives it unique properties, especially with respect to electromagnetic fields.
What do you mean exactly? What are some of these unique properties?
Imagine if you have a neutral gas and you apply a magnetic field, this would essentially do nothing. The plasma, there the little particles would start running circles around the magnetic field lines, and the electrons would do it in the opposite direction as the ions. Then they would start drifting in some directions, and you can capture plasma with this. This is also my field of research, and this is one way how to achieve nuclear fusion in the end.
Can you elaborate more on this? How is this connected exactly to nuclear fusion?
Yeah, so it's not directly related. It's rather, let's start from the other end. In nuclear fusion, you need to bring ions very close together. And in order to achieve this, you have two options. Either you shoot them together for a very short time, or you do this in a kind of steady state way. And for this, you need a very high temperature.
So for this, then plasma is ideal because you have a high temperature and then the particles are, I don't know, closer together than on average? Or how does it work?
Yeah, so the high temperature you have in a plasma, so because of this high temperature, you can only have matter in the plasma state, because if you heat matter so much that the conditions for fusion are fulfilled, you will separate the electrons and ions because you're higher than the binding energy. And why is this high temperature needed? I also elaborate. You need to bring the ions close together because they repel each other usually. They are positively charged. And if some of them are very fast, then by chance they could hit each other like two cars crashing at very fast speed. And then they would get so close together that other forces take over. And this is in this case the strong nuclear force that would then fuse the atoms.
And so the temperatures needed to start the fusion are enormously high, right? So in plasma, you can heat it up that much?
Yeah, so the temperatures are not an essential issue right now. So we can reach temperatures in the lab of hundreds of millions of degrees, which is about what you need. And this is higher than the temperature inside the sun. So people say it's the hottest place in the universe even. That's not exactly true, but maybe in the solar system. So, but that's not all. You need not only a high temperature, that's a necessary condition, but you need also a high pressure. And to achieve both high temperature and high pressure at the same time is a challenge that is still ongoing.
This is also what you research on?
Yes, this is exactly what we do. So to capture or to confine the plasma at a sufficiently high temperature and pressure, and to avoid instabilities forming, because if you can imagine if you put a high pressure on something very hot, this can generate a number of unstable conditions, and then there are ways to stabilize them, of course, and we are more or less on this specific topic to study the side effects again of the medicine against the instabilities.
So what are some of these ways to stabilize the plasma?
Essentially, in magnetic confinement fusion, you have two types of devices. One is called the tokamak and the other is called the stellarator. And the tokamak is a very simple device. This is why it's now preferred as a power plant by the mainstream. And it's essentially, it looks like a donut. So it's axisymmetric. It has no three-dimensional features. It's completely symmetric if you go around it. And some of the instabilities that appear in a tokamak, you can mitigate or even suppress by adding a small non-axisymmetric perturbation. And this is our topic, essentially.
What about the stellarator instead?
The stellarator is the other extreme. This is completely non-axisymmetric, but it is inherently more stable than the tokamak. However, it's hard to build in some sense because you need to make very complicated coil shapes. So you generate a magnetic field with electromagnetic coils, and also the strongest electromagnetic coils again on the planet or something. So this is really the limit what you can reach technologically, and it's easier to do this in a simple geometry. However, in the stellarator, you have also many more options to optimize it. So you can play around with the shapes, and this is our other topic, what is of interest, to help this optimization of the stellarator and some metrics which are important there.
So then which of those two do you think will be the first nuclear fusion power plant?
So to quote Hartmut Sohm, who is an expert on the topic, and he said probably the tokamak will make it first, But this will spark so much interest in the topic that in the end it may be the stellarator taking over because everyone gets more funding and it has some distinct advantages.
But what are still the challenges? Because, nowadays it's not really used. So power plant based on fusion reactors are not really used. So why is it so? Like, it's because we still don't understand the physics, or we're not sure about the confinement. What are still the challenges?
So there are several challenges and several things which might have run better in the past, especially with respect to ITER. Some people know it. This is the biggest tokamak being built currently and always delayed. Every 5 years it's delayed by 5 years. And this is partly due to politics, because it's a huge international project where they agreed that every country should deliver all kinds of components which should then fit together, and this is a mess, honestly speaking. Now they have a new management again, and they are in their new timeline, so the hope lives that 2035 we have real significant fusion power from ITER. Yeah, and the other challenges are then to a power plant, because ITER is still an experiment, that you should qualify the materials with respect to the high neutron loads you generate from fusion. And this is a different kind of load than you can now do in a fission reactor with any other source of neutrons. So you should essentially build a fusion reactor to test the materials that are useful for a fusion reactor. And this is another project. This is now called the volumetric neutron source, and this is being prepared in Europe. And yeah, and about who will be the fastest with some significant fusion power will probably be China or USA, a private endeavor.
So not Europe, probably.
So ITER is not a European project, it's an international project, even though kind of everyone leaves and the Europeans have to pay the rest. This is a bit the feeling. But it's not that bad, actually. I mean, everyone relies still on ITER, so or the private startups, or also in China, they are part of the ITER consortium, and it's a kind of hub where everyone works together, and this is also the main meaning of ITER, no matter if it will now take longer or shorter, and then the ITER partners themselves do their own projects, which will maybe overtake it.
Can you maybe comment about the difference between fission and fusion, nuclear fission and fusion? Because what we hear nowadays is fusion is very convenient due to the waste confinement, which is easier. So what's the difference between the two processes, and why is fusion safer?
Yeah, fission is not inherently unsafe, except when you start an uncontrolled chain reaction, which does not exist in fusion. Because if you make the plasma even hotter, then the reaction rate of fusion will decline. It will not have a runaway reaction. So that's inherently safe in contrast to, I think, all fission reactors that are viable. And the other thing is about the waste. So fission generates high active waste, like plutonium or isotopes from heavy elements that will have to be stored safely for 100,000 years. And in fusion, you generate low to medium active waste in a larger volume even, but this you will have to store only for 100 or 200 years.
Interestingly, also, there's fission and fusion, which are two different processes, right? In one, you break up the atom, in the other, you melt them together, sort of, right? Or the nuclei. And both give you energy. Naively speaking, that would sound like a contradiction. So what is the issue there, or how does this work?
Yeah, as in many topics, the sweet spot is in the middle. So there are two extremes in the periodic system of elements. These are the very light elements and the very heavy elements. And both don't like essentially the way they are. They all would in the end like to be iron, which is the most energetically stable configuration. So if you overcome this barrier, and in the case of fission, you also have to initiate the fission. This is why you need also neutrons, and you get the chain reaction then. So then they will break up into more energetically favorable elements, and in the fusion you have to overcome an even larger barrier, which is this Coulomb barrier, which we talked about, this repulsion, and then you will also get even more energy per reaction, but it's harder to achieve.
And for the fusion, it's also hard to extract the energy, isn't it?
It's not so hard actually. The main concept will be just to attach a usual power plant. So the fusion will generate alpha particles and neutrons, and those eventually will hit the wall, and the wall will become hot, and then you have a conventional power plant.
But you also need very strong conductors, which have to be very cool, very strongly, right?
Yeah, that's an issue. So you have 100 million degrees in the center, then you should have essentially minus 200 something degrees at the superconductors, and then you have room temperature, and this within a few meters.
Can you maybe comment about this all this hype that was generated by this experiment a few months ago? What was 1 year ago, and something when there was this people managed to fuse something in the lab with a very low temperature, or am I wrong?
So what you are talking about is cold fusion, I guess.
Fusion, yeah.
I'm not sure. This pops up from time to time. So essentially, there was a hype in the 1980s about cold fusion, and it turned out to be kind of fake. So, I mean, physically speaking, it's if you don't have a way to explain this and you have no accurate measurements, I would not believe it. And they had neither back then. I don't know about this specific cold fusion in the near past, but I would be very skeptical. One thing that actually worked very well was the laser fusion, but this is a serious thing. This was also like 2-3 years ago now.
Can you tell us more about this?
Remember at the beginning I said you can either shoot ions towards each other very fast for a short time or have it in a steady state way. So now we talk about the first way. And essentially you shoot a pellet from many sides. You shoot at it with X-rays, and these X-rays are generated by an evaporating capsule, which you evaporate with a lot of lasers shooting at it. This is the mechanism. And this is more for defense because it is a mechanism that's similar to a fusion bomb. So with the other way I explained before, you cannot use neither directly nor indirectly for military use. With this laser fusion, there is an indirect military use in the sense that you can keep your simulation codes essentially validated, which you can also use for a fusion bomb. So this is why it runs under the Nuclear Weapons Stewardship Program in the US. However, you can also generate energy out of it. So a bit like fission, right? In fission, you can generate also plutonium. But you cannot use this directly as a weapon or either. This is why it doesn't fall under any proliferation treaties. But it also gets lots of money for this reason. And they managed to get more energy out than they put in for the first time. And this generated a bit of a hype, which is now ebbing away. But this helped also magnetic fusion to get a bit, which is a completely different concept, but to raise some funding, at least, also privately.
For the theoretical work you did, do you also collaborate with experimentalists to check these results, sort of? Or
Yes, very much. So we work primarily with experiments and very close to experiments in Germany, mainly because we think that theory decoupled from experiment is a dangerous thing. And of course it's hard because you should explain experiments and usually your calculations don't match very well. And so then both sides have to adjust and measure more accurate or try different things and improve the models. Yeah, so it's an ongoing challenge, I would say.
What is the result you obtained that you're most proud of or that most amazed you?
The result I obtained that I'm most proud of is a very theoretical result on how to trace these little ions in a fusion reactor in a computer simulation, but do it in a way that you don't lose any energy or momentum in an artificial sense. And this was a well-known technique for all other mechanical systems except for these very special ions in the fusion reactor. And we managed to break this nut. And it has also a practical application in the optimization of stellar reactors, where you can now run at least 3 times faster your simulation at the same accuracy.
That sounds amazing.
Thanks.
So theory is not so dangerous after all.
No. There's no contradiction. That's maybe the lesson from this. This is why I like this result. You can do very deep theory, which is very useful.
What are the other lines of research that you are at the moment interested in?
So we are now expanding a little bit into astrophysics, where surprisingly, or not so surprisingly, because most of the universe is made of plasma. This I forgot to mention. So similar equations are used, and we can learn from each other from the two disciplines.
That's interesting. Most of the universe is made from plasma. Can you elaborate on that?
Oh, you just have to. I read it in a book. I don't know, but you can do the math. Think of the whole cosmos, and it's not so hot essentially, but it's also how to say. So stars, everything near stars is plasma, of course, but also the interstellar, interplanetary space is plasma. Because it's very vast and the charge carriers are free, and the concept of temperature is maybe not so good anymore, but it has a temperature essentially, and it is a plasma. Everything between the sun and us you can see as a plasma.
That's interesting. Maybe a more personal question at this point. What is your way to balance work and private life as a professor?
So the best way to balance work and private life...
Your best way.
For myself personally, I would say I had a little son in January, and he is now one main center of attention besides science, and this is a great motivation to just say there are more important things in life than just formulas.
That's a very nice answer. Is there something you want to mention we didn't ask? Maybe something that about your research or the topic itself that you think it's important, but we didn't cover so far?
I would say very generally, I hear every time people talk to me about fusion, especially physicists, they say, this is 50 years in the future. And to me, it's really important that at least please check the facts, what's going on right now. Fusion may be nearer than you think.
So you foresee a future in which humanity, the activities that we do are powered by energy coming from nuclear fusion?
Definitely.
Oh, that's inspiring. Christopher, thank you, and see you next time.
Thank you very much.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.